So average rate of change, just another word for slope. You've done this a whole bunch last year and in Algebra 1. So nothing new here. So thank you. The first example is a little bit more of writing the equation of a line. So they give us a point, and they give us that our line has to be parallel to. Now, you probably didn't do much of this last year. You probably haven't done this since geometry, a little bit maybe, or Algebra 1. But again, in order to write the equation of a line, we need two things, a point and a slope. Well, we have the point. This is their way of giving us enough information to figure out the slope we're supposed to use on our own. So if you want two lines to be parallel, same slope, correct. So you need our line to have the same slope as this line. What is the slope of this line? 2. Is it 2? Negative 2? How do we figure it out? Connor, why are you saying 2?
You can put you can add the y to both sides and add the 1 to both sides to get isn't slope-intercept form.
Yep, and Taylor, why are you saying negative 2?
I don't know, I just kind of speak it quickly, so.
Well, I think you were probably moving this over in your head, but then you have to renegate it because of that negative sign. So add y, so 2x equals y minus 1, add your 1. So once you get it in y equals mx plus b, it's pretty easy to see that the slope is 2. And so that's the slope that we will use. So our point slope format, just y minus the y coordinate of 1 equals your slope of 2x minus negative 3 becomes x plus 3. Now that I'm thinking of it, on last night's homework, the solutions in the back of the book, did it have any of the equations written like equals 0 like we talked about? Oh, okay. Oh, it's somewhere in the book that comes up, but I guess it wasn't last night. So that's point slope form. Does it say what? No, it doesn't specify that it wants it in any specific format, so you might as well just stop here. Okay, what about perpendicular? The opposite reciprocal. So this line that we want to be perpendicular to, this line has a slope of negative 1/4. So our perpendicular slope is going to be positive 4. That's my perpendicular sign. You should remember that from geometry. So the perpendicular slope is positive 4. And then again, we're just writing in point slope. Y minus negative 5 equals the slope of 4, and then x minus 3. Any questions as to where any of this is coming from? Okay. So average rate of change. Again, like I said, you did this last year. It's just the change in the y over the change in x. In Algebra 1, you write y2 minus y1, right? But in Algebra 2 and beyond, it's f of x2 minus f of x1. That's really means the same thing as y2 minus y1, but just the more advanced notation over x2 minus x1. Okay? And again, we're going to start talking more about kind of how this relates to calculus, because the average rate of change, so on average from point x1 to point x2, it's changing with a certain slope on average. Sometimes the slope is much higher than that average. Sometimes the slope is lower than that average. But on average, all of these instantaneous slopes, if you average them out, will be that right there. Okay? So again, kind of just playing into the idea of the fact that on any curve, the slope is constantly changing. All right. So given a function, this one x squared, find the average rate of change along the interval from 0 to 1. So how do I start this process? Lily W. Right. These are both the x values. We're talking about on some graph, and I know what y equals x squared looks like because it's the parent graph. So from 0 to 1, that's giving us our x-axis numbers, only our x coordinates. So she's saying plug them in. So you plug in 0, you get 0. Plug in 1 squared, you get 1. Now we have the 2 points. Now we can find the average rate of change. So 1 minus 0 over 1 minus 0 is 1. So looking at my little sketch here, if I just connect this with a straight edge, there's my average rate of change. Now I'm going to go from 1 to 2. What do you think is going to happen to the average rate of change compared to this one? Thank you. It's going to increase, right? This parabola has gotten steeper between 1 and 2 versus 0 and 1. So we just confirm that. Again, from 1, that's the 0.11, to 2, that's the 0.24. Slope formula, 4 minus 1 over 2 minus 1. We get 3. Okay, of course it got bigger, steeper, as we thought. How about from negative 2 to 0? What's our prediction there? Negative, okay. How about the magnitude? Is it going to be more or less, this being a magnitude of 1, this being a magnitude of 3? So forget about the negative sign, although obviously that's negative. Is the magnitude in your prediction going to be more or less, or what would you guess based on the visual? What do you think, Taylor? In between? Did you already do it? Right, because these are symmetrical on either side, I'm actually just going to use 0 to 2 on the right-hand side. So it's steeper than this one, but not as steep as that one, so somewhere in between. Yes? But it's going to be the negative side of things. So we have negative 2, comma 4, and 0, 0. And then throw your slope formula in there. So we get negative 4 over 2, which is negative 2. So yes, it's negative, as Jack said. And yes, the magnitude is somewhere in between those other ones. Because again, it's on average, right? So from 0 to 2, it was 1 initially, and then 3. So on average, that was 2 if you go from start to finish. Okay? And on this last section here, get your calculators out because we're going to need these. This is more of the conceptual approach. So there's a word problem attached here. Average velocity. Okay, depending on who's taking physics and not, this may look familiar. But your average velocity is your speed, essentially, is your change in position over your change in time, which is really distance over time, right? So we know this, distance equals rate times time. We kind of used that recently in our word problems. And if you just solve for rate equals distance divided by time. Same thing. Rate is velocity. Distance is your change in position. T is your change in time. But this kind of portrays it as this average rate of change problem. So your position at time 2 minus your position at time 1 over your time 2 minus time 1. So we're going to look at this particular word problem on a couple of different intervals. You can see the decimals show up, so that's why we needed our calculator. Here's our formula for position. So S of t equals 5t squared. So we need to find our position at 2 seconds. What's that? 20. Our position at 3 seconds. What is it? 45. So our average rate of change, meaning our velocity, between 2 and 3 seconds. Is 25. Our distance is in feet, so that 25 was in feet per second. Okay? Then we're looking at our average velocity from 2 to 2.5 seconds. So I want you to go ahead and do that one. Again, have your calculators handy, and then same thing with C. And then I'll do it as well, and you can check your answers when you're finished. Raise your hand if you're done. Okay. Take another minute to finish up. And then we're going to explain. Okay, what did you get for part B? Kendall. What were the points that you got? Okay, good. And so, Josh, what's the average rate of change on that one? Good, 22.5 feet per second. Any questions on that one? And on C, what did you get Stephanie. Good, 20.05 feet per second is what I got as well. So, here's what's going on here. Initially, well, I'm going to graph this for you so we can kind of focus on what's happening. There's my function. When I set my window, my x-coordinate is my t, right, time. So there's no use in going negative seconds, right? I'm going to go from 0 to seconds to 5 seconds because I'm only really looking from 2 to 3 at max, but I'm going to go 0 to 5 on my time. And my y's, this is all giving me position. My maximum position is 45, so I'm just going to go from 0 to 50. So here's what this graph looks like. So we found the average rate of change from 2 to 3 initially. So here's 2, and here's 3. Okay? And so, I'll draw on that on the board. So from 2 to 3, we found that the average rate of change was that 25. Okay? And then from 2 to 2.5, so here's 2 again, but then we want 2.5, which is here. Got a little bit less steep. We all agree on that? Okay. And the number reflects that. It dropped out at 22.5. And then we did 2 to 2.01 seconds, which, I mean, I guess would be like right there. Right? And we got, what was that third number we got? 20.05. So, how does this relate to what we've been talking about? What does this connect to that we've talked about recently? A new concept. Right, so it's that similar concept of the difference quotient, which again, we were calculating and getting, when simplified, it would give us an expression to use to find an instantaneous slope, meaning the slope at a very specific point. What point is this gradually getting us the slope at? At x equals what? At what location, x equals what, are we gradually moving towards finding the instantaneous slope right at that value? 2. Because we're going from 2 to 3, and so our h value is kind of like 1, right? And then you're pinching h in a little bit, so then from 2 to 2.5, your h value is pinched in to only being a half. And then by the time we get down here, our h value is pretty much 0. But yet it's not 0, it's still slightly large enough, this little gap here. There is some gap there that allows us to still do the slope formula. But as we progress towards pinching back towards 2, we're getting closer and closer to the absolute exact velocity at that moment in time, at that 2-second mark. Does that make sense? Okay? So if we were to do the difference quotient with this, shoot, Josh, can you go erase that? I'm going to do the difference quotient with this down here. So f of x plus h is going to be 5 times x plus h squared minus f of x, so minus 5x squared. You with me? All over h. We're going to simplify this. This is going to be x squared plus 2xh plus h squared, and I have to distribute the 5. So that's going to be 5x squared plus 10xh plus 5h squared minus 5x squared all over h. Your 5x squareds cancel, and then both terms are divisible by h. So we get 10x plus 5h as our difference quotient. Now, X is the location at which we're trying to find the slope, yes? Okay? This is pinching in towards 2, so we're looking for the instantaneous slope at 2. So 2 will go in for X, and H is pinching down to 0, right? So we will assume that the H is 0, and we are looking for the instantaneous slope at 2, and we get 20, which is obviously very close to what we got here. It's not exactly the same, because right here, what is technically our H value? Right, 0.01. So if we plugged in 0.01 for H, we would get exactly what we got right there. Do we follow that? But the fact of the matter is, you could do this down to 2.00000000001 seconds and beyond, and the actual instantaneous speed, these numbers would keep encroaching on 20. They would keep getting closer and closer to 20 because 20 is the actual speed right at that moment. Does that make sense? We always eventually assume H is 0 because we want to pinch these 2 points infinitely close to each other, which means H is essentially 0. And this is why when you were doing the difference quotient, where we had to simplify always until that H was not in the denominator anymore, which on quadratics always kind of worked its way out naturally. But on some of the radical ones that you were doing the difference quotient on, remember we had to rationalize that numerator, and that eventually allowed us to cancel the H in the denominator. And the reason for canceling that H in the denominator and taking the difference quotient all the way through until that happens is so that we can safely assume it's 0, and so that we can find the instantaneous rate of change. Okay? Conceptually, does that make sense? It's hard to really take notes on that. You just kind of have to listen closely to that description. But are there any questions on that? Okay. For the sake of this chapter, and especially your chapter quiz that's coming up on Monday, you're not assuming H is 0 when you do the difference quotient. You'll leave your difference quotient like this. But I'm just sort of building my case for kind of where this heads and why we do all of this. Okie doke? Any questions? I think we're done.